This is section 6.3. It's integration by parts. We start out with the product rule in integral form. So if you want to take the derivative of uv, it's equal to first times derivative of second plus second times derivative of first. If we integrate both sides with respect to x, and rearranging leads to the integral equation. Let's see what they done here. They've left the u dv dx on this side, and they've subtracted the v du dx over to get this statement. But then they've integrated both sides. Now when you integrate both sides, the integral of the derivative of uv, well, that would just be uv. And then if you integrate v du dx, well, it's not the integral of the derivative, so it just stays. This equation is written in the simpler differential notation. We obtain the following formula. So here's the formula you need to know. In order to integrate u dv, it's equal to uv minus the integral of v du. And so when we start working these problems, we're going to pick a u and we're going to pick a derivative. So we need a function and a derivative when we do these problems. Here's example 1. We're going to follow this formula over here. We're going to let u equal x, and we're going to let dv equal the cosine of x dx. So now we have everything in the formula accounted for. We have the x, excuse me, and we have the cosine x dx. Now we're just going to follow the formula. We're going to follow this part right here. Well, first of all, we have to find du. We need u, v, we need v, and we need du. U equals x, of course. Du equals, in this case, 1 dx. And then we're going to back up this one. This is the derivative. We're going to back up to the original function. So, oh, I don't want dx there. I want dv. So v equals the sine of x. If we take the derivative of both sides, we get right back to where we started. Now the formula says the integral of u dv, of u, which is x, dv, which is cosine of x dx. The integral of that is u times v, so we have x times the sine of x, and then minus the integral of v and then du. Well, v is sine of x, and du is just dx. And now we have something that we can actually take the antiderivative of. So the answer is x sine of x plus cosine of x, and then of course plus c. In this example, we're going to have to do this process twice, and we want to let u equal x squared. We want to let u equal a function that if we take the derivative enough times, we will get to 0. So dv equals e to the x dx, and once again everything in the problem is accounted for. Du, the derivative, is equal to 2x, and v in this case is equal to e to the x. And we follow the formula. We have u v minus the integral of v e to the x du. So then times 2x dx. I should have a dx here when I took the derivative. Well, we still don't know what the antiderivative of this is, so we need to let u, the second u, equal 2x, and we'll let dv2 equal e to the x again, e to the x dx. So everything in the problem is accounted for. So the derivative of the second u equals 2 dx. And if we back up or take the antiderivative of dv, we get v equal to e to the x again. Now we're going to bring this down with us. So we have x squared e to the x minus, we use parentheses because we're minusing this entire antiderivative, or that entire integral. So we follow the formula again. This time it's u2 times v, which is 2x e to the x minus the integral of v du, so 2 e to the x dx. And now we finally have something that we can actually take the antiderivative of without a special process. We have x squared e to the x minus 2x e to the x, and then plus, I can pull the 2 out, and the antiderivative of e to the x is e to the x. So we have 2 e to the x, and then plus c. In example 3, we're asked to solve the differential equation dy dx equals x natural log of x, and we have an initial condition where x is 1 when y equals -1. We're asked to find the y if we're given the derivative. To solve the differential equation, we're supposed to back up. So we're going to take the antiderivative of both sides, and we're going to do this by parts. We're going to let u equal, but I don't know how to take the antiderivative of natural log of x, so I don't want that to be the dv. I actually want this to be the u. So we have natural log of x, and dv is going to equal x dx. When we take the antiderivative, we're going to have a dx here. The derivative of natural log is 1 over x dx. And I don't want dx. I keep doing that, don't I? I want dv here. So v equals 1/2 x squared. So the antiderivative is uv, which will be 1/2 x squared natural log of x. There's the u, the v, minus the integral of v du, which is 1/2 x squared times 1 over x. Oops, why did I write it 2? One over x dx. There's the v and the du. This is 1/2 x squared natural log of x, and this simplifies to, well, I can put the 1/2 out in front. This simplifies to x. X squared over x is just x. And then y equals 1/2 x squared natural log of x. And we can actually take the antiderivative of x. That'll be minus. Now, the antiderivative of x is 1/2 x squared. We already have a 1/2 out there. That's going to make the answer a 1/4 x squared, and then plus c. Now they give us an initial condition so that we can actually find the c. And the y is -1 and the x is 1. So we plug -1 in for y and 1 in for all the x's. 1 times 1/2 is 1/2. And we have the natural log of 1 minus 1 times 1/4 is 1/4 plus c. Well, the natural log of 1 is 0. That makes this -1 equals -1/4 plus c. If we add over the 1/4, we get -3/4 equals c, and we can finally write the answer. Y equals 1/2 x squared natural log of x minus 1/4 x squared, and then minus 3/4.